Okay, so I've just been introduced. Apparently you now know who I am, so I can skip over that part of the talk. And as you can see, it's about color. CSS4 Color, CSS3 Color is what you already use. It's boring stuff. Well, I was co-editor of that too, but you all know about that, so that's boring. So that's me. We already established that, and that, and that, and that, and that. But the CSS4 Color part, that's the interesting thing. That's what I'm here to talk to you about today. Actually, I lied. I'm not going to talk about CSS4 Color except for like 1 minute at the beginning and 2 minutes at the end, because here's the problem. Okay, this is what we have in CSS4 Color. As you can see, we have a chroma here, a hue angle here. We've got a fullback color and an alpha, right? Understood? I can just stop now, right? Yeah, the thing is, you can look at that, you can see what the syntax is. What you don't know is, what does it mean, Chris? Why would I ever want to do this? So what this talk is actually going to be about is firstly some basics about color. Then we're going to talk about how you measure color. Then we're going to talk about CIE Lab, which is the cool thing that I'm telling you about, that you'll understand why you want it once you've seen it. Then I'm going to talk about displays and print. Does anyone here, well, okay, everyone here uses CSS. You all use CSS for websites. Does anyone here use CSS for printed material as well? A couple. Yes, okay, good. Well, I'll talk about that briefly. And then lastly, as I said, we'll get on to CSS4 Color, where I show the relevance of all of this stuff. So, first thing, what is that? What is this device here? A prism, right. What does a prism do? It reflects light, and what's the result of that? It makes a rainbow, right, it makes a rainbow. Okay, so we've already established that you already know all about light. You know that it's made of different wavelengths, and that they go through glass at different speeds, and therefore you can turn white light into a rainbow, and the white light actually consisted of all those colors originally. So this is good, we already know something. Light is the range of wavelengths visible to humans. I mention humans because, like, if you're a bumblebee, you can see some ultraviolet, and if you're a snake, you can see some infrared and so on. So there's nothing specific about those colors. Those colors don't exist in nature. Those colors exist in our brain, in our eyes. It's a human, colors is a human response. Or at least the colors that we care about. We don't actually know much about bumblebees and snakes and how they feel about color. So here is a rainbow. Don't worry about the numbers, but it's roughly 380 nanometers to 700 odd nanometers. That's the range of wavelengths that we can see. And as you can see, we've got all the other colors in between. So that's the visible spectrum. The next thing we need to know is you have, don't worry about all the labeling here. There's only one thing you need to know about, which is the retina, which is this set of nerve cells at the back. The rest of it, you can just assume it works. And for the purpose of this talk, that's it. So what's the retina made of? Well, it's made out of these cells, and these cells, and these cells, and then a big black layer at the back, which basically stops the light. Oh, the light comes in from here, this way, goes through all this wiring. Who designed this stuff? Goes through all this wiring, and then hits a black layer there, which it gets absorbed. And we've got rods, which look roughly rod-like, and cones, which someone in a fit of imagination, looking through a microscope, decided were conical-ish. And then you can see that they have basically connections to these pink cells. This one is connected to 3 of them, and this one's connected to 1, and etc. And there's also these blue ones which connect groups up laterally. So there's basically, think of this as a circuit. There's lots of things happening here, even before we go, oh, and these form the optic nerve. These come out the back of your eye and go off to your brain. So even before the signals have left the eye, lots of stuff has happened to them. It's actually really complicated. There's groups, Sarah was talking about animation, said that our human visual system is particularly good at detecting motion. It is. The parts on the outsides of our eye are really good at detecting motion, really poor at detecting color. The bit in the middle is actually, it tends to average things over time, so you don't notice changes fast, but you're really precise on little color shifts. So we have 2 completely different visual systems which we use in tandem to build a mental model in our head of what the world is. Okay, great. That's fun. So let's have a look. There are 3 different types of cones. And if you read a BAG textbook, they will tell you they're called red, green, and blue cones. No, they are not. Here is the 3 cones, and you can see that this one has its maximal response in yellow, this one in yellow-green, and this one in bluish-violet. So we'll call them L, M, and S for long, medium, and short wavelengths. You can also see that these two are pretty much the same, and this one hardly does anything at all. So let's look at that on a logarithmic scale. Now we can see much more. Yeah, these two are definitely almost the same. And now, if you were building a system, if you were building a piece of electronics to measure light, you would never design it like this, right? These two, you could probably replace that with just one sensor, because they're almost the same. You would have nice sort of bandpass functions like this to keep nice. No, our eyes aren't like that at all. This one, in fact, all of these 3 cells have evolved from the same cell. They've just diverged and got different sensitivities. So we now know that we have these, and these do not give us a red, green, and a blue. They're giving us these sorts of strange values. And then all of that information goes off to the brain, to this bit at the back. Actually, it goes through a bit here in the middle, which I missed out, but never mind that, the lateral geniculate nucleus, and then it goes to the human visual cortex over there, where we get this entire visual processing happening going on. So let's go back from all the complicated things to stuff that you already know about color. Now, what I want you to do is, you see the black dot in the middle there? I want you to look at that. Try not to let your eyes move, and I want you to look at that for about 15 or 20 seconds. Just keep looking at it. Don't let your eye track around. Just keep looking at that same black dot. 15, 20-ish. Do you see anything? Green, right. That's weird. That's a white slide, completely white slide with a dot. Let's do that one again. Oh, different color this time. So look at the black dot. Try not to let your eyes move. Just keep looking at the black dot. 10 seconds. 15. 20. Ooh. Yes. So these are called opponent colors. Why are we seeing this? What actually happened is the cones in your eyes use a particular pigment which absorbs light. And over time, if it keeps getting the same input, it kind of bleaches out, it gets tired. And then if I suddenly switch to white, you'll see basically the inverse of that. You'll see the opponent thing. And what this tells us is that all those nerves, what they're doing is they're producing opponent colors, colors which are opposites of each other. And we're very good at detecting changes where something changes to its opposite color. And you'll see the relevance of this later on when I get onto LAB. Next thing you need to know, what color is this? Yellow, right. It's a piece of white paper, which I took a photograph of in a hotel room, but I switched off the auto white balancing on the camera, so it came out as yellow. And if I was to do the same thing outside, it would come out as light blue. But if you were with me in the room looking at that, you and I would look at it and say, this is white. Why? Because we evolved to be in a constantly changing visual environment. The sun goes behind a cloud, and it takes the light level down, and it changes the color balance, and none of that is relevant. Our eyes will just filter that out, and we will just see the scene as having shifted slightly. Not all of the colors changed, right? So our eyes are constantly doing white balancing. We adapt to whatever we think is the brightest, most white-like white, and all the other colors shift to adapt with that. And if you don't do that, then you get things like this, where people have wars on the internet about exactly what color a dress was. Okay, so color. What we know about color is it's a subjective sensation in the human brain. And it's caused by visible light acting on the human eye and then going through a whole bunch of layers of neural processing. Okay, that's a great definition. That tells us about color. What? What can we do with this? I mean, it's really complicated now. If we want to know what a color is, we're going to have to measure how bright it is at every different wavelength, like a spectrum, and then we're going to have electrodes in the brain and measure all the impulses from all the nerves and put it all together, and it's going to be really complicated, and we can't possibly do this. Actually, we can. It turns out to be simpler than that, simpler than you might think. We can treat the entire visual system as a black box. We can say, here's the inputs, tell us what the outputs are like, and we can build a model from that. So, next stage, measurement. That was all basics. That was all easy, simple stuff. Woohoo. So, measurement. You want to measure color. Let's start off with this. This is a spectrum. This is a graph of how bright a particular thing is at all the different wavelengths, from red through to violet. And you can see this has got all these peaks. So from that, you can tell what color it is, right? Any guesses what color it is? I couldn't tell you, frankly, looking at this. This is actually white. It's a light bulb. From that, you can't tell. You can't tell at all. And you can have a totally different spectrum that also looks white or green or whatever the color it was. Just the spectrum alone doesn't tell you what color it is. What can we do about this? Well, looking at that graph, we can see that we actually know that brightness responds like this. If in the greens and the yellows, we see a lot. We see those colors as very bright. And off here in reds, we see it as very dark, and the same for blues and violets. So we already know this. This is one response that our eye produces. And in fact, there is a channel coming out of our eye into the brain, which is basically how light or dark is it in a particular area that we're looking at. So that's one thing. Remember, I showed you these cone responses, so you can see where that graph comes from. It's basically you just add them up together. Good. Whoa, I've gone back. Why did it do that? It's gone right back to, oh, tell me that I'm not in a loop. Please don't let me be in a loop. No? Yes, good. Okay, so visual matching. You can have different spectral things, and they look the same, even though the spectra are different. And we can use this to our advantage. So here's an experiment. This was done in the 1930s. So what we have is two ground glass blocks and a person looking. And on this side, we have three lights. This one is 700 nanometers, so it's a dark red. And this one is 546, so it's a yellow-green. And this one's 430, so it's like a violet color. These were actually made with mercury vapor lamps, so they could do the same experiment in different laboratories and always get the same result. And on this side, we have the mystery light, which is actually a diffraction grating. You make a rainbow, you take one tiny slice of the rainbow, you show that. And then you say to them, they've got three knobs or sliders or whatever, and you say, match that color. Keep moving these until you get the same color on both sides. And then you do it again for a different wavelength, and so on and so on. And you have subjects who have an awful lot of patience because they have to do 700 of these experiments to get the result. So, you'll notice I've also got another set of these lights on this side. Why is that? It turns out that sometimes, for some colors, you could not match them at all, right? You'd got red turned all the way down, and you really wanted to make it less red than that. And the way you do it is you cheat. You put the colors on the other side, and you make the color trying to match more red until it matches. That's fine. That's just a negative number. Negative numbers aren't very popular in the 1930s because they're doing all their math and slide rules, and they don't want that. So they got this table of how to match with these three particular weird lamps, and they convert it to something called XYZ. CIE is just the organization that did these experiments. But okay, XYZ gives you three numbers, and if two colors have the same XYZ value, they will look the same. They will be the same color to you. So it gets rid of the negative numbers. Also, Y is the luminance. That was the graph I showed you of how bright particular colors look. So it gives you the luminance straight away. It's also an additive color space. What do I mean by that? If you have, well, we do have. There's a yellow light shining there, and there's a purple light shining there. And if Martin was here, he could make these move in together so they merged on the stage to produce a color. And if I had the XYZ value of that light and added them together, it would tell me the color of the mixture would appear in the middle. I could actually predict it. You can do math with XYZ and get the right result. So that's cool. That's useful. There's some problems with XYZ. Here is a graph of luminance from whatever it is, 100 to 0, and you can see that mid-gray is away over there, which is not very handy because it would be kind of useful if it was in the middle. So luminance is not what we call perceptually uniform. Another thing with XYZ is that white adaptation isn't handled. Remember I showed you the piece of white paper and how we always see it as white, even if it's a yellowish lamp or if it's bright bluish daylight or whatever. Not only does that change white, it changes all the other colors as well. So let's have a derived system. We'll take the XYZ and we'll change it a bit. We'll take the Y component and we'll put a bit of simple math on it so we get a scale which grays in the middle. Like that. There. That's a plot of L from 0 to 100, and 50 is right in the middle. Great, excellent. Much better than that. Now we have A and B. So we did these opponent matching experiments together, and we find that this color here, ooh, there we are, that color here, if you stare at it for a while, you'll see that color. And this one, if you stare at it long enough, you'll get that color, and so on. So these are the two axes for colorfulness. Put that together, and you have a nice three-dimensional color space with lightness going up there, and A and B. Now, the trouble with that, actually, you try to match a color using RGB, right? You've got 3 sliders, and you're trying to get the color, and it doesn't really work, and you're like, oh, how do I actually get there fast? It's difficult. It'd be much easier if we looked at the angle around from, say, the A-axis and just went around like that. How far around and how far out? So we can take LAB and just take it from, take it into a polar coordinate system like this, and then we get that. That's nice. So now we have L coming out of the screen like this, lightness, and we've got hue as an angle. And at this point, some of you are thinking, hang on, I've seen all this before. I've seen it before. We've got HSL. It does exactly the same thing, doesn't it? You've got white, and you've got black, you've got an angle, you've got a saturation. Have any of you ever noticed that if you mix up blue, right, in HSL, it has a lightness of 50%. And if you mix up yellow, it has a lightness of 50%. And does the blue and the yellow look the same lightness to you at all? No, the yellow is much brighter, the blue is much darker. If you do that in LCH, then it actually corresponds to how light it looks. The yellow will have a lightness of about 70, and the blue will have a lightness of like 30 or 20 or something. In other words, it corresponds to what we see, it corresponds to what we can measure. Good. So now you know that LAB and LCH are basically the same thing. One is polar, one's rectangular. It's actually a measured color. You can get physical devices that you stick on something and measure the color. It gives you a readout. It's good, so we can do that, but now we need to display these colors. How do we do that? First of all, you characterize the display. You measure the color of red, and then of green, and then of blue, all separately, at all the different levels from 0 to 255. And then you calibrate it, you correct the imbalances. You say, okay, at this value you've got this much light, and at this one you've got this much light, and you measure it so that the grays don't have a little bit of a shift here, a little bit of shift there. They're actually neutral grays all the way along. And you also have a known white point. Whatever the white point you want to be as a standardized white point, you set it to that. Now let's talk about the gamut. The gamut is not to be confused with gamma. Gamma is the shape of the transfer curve. Gamut is the range, the volume of colors you can have. So you've got LAB, and you produce a volume there, which is the range of colors. A tiny one will not be able to display very many colors, and a broad one will be some fancy pro monitor that can display lots of colors. You've probably seen this diagram, by the way. If you ever look at high-end monitors, it'll have this, and it'll have a little triangle here, and it'll say this is better than this because it's got a big... This is rubbish. Don't ever trust this diagram. This is a chromaticity diagram. It's a slice of XYZ. It is not perceptually uniform, and remember I told you perceptual uniform is the important thing. So any calculations you do in this space will not give you correct answers. Ignore that. Instead, what you want is that. That's a three-dimensional shape, which I'm going to try to manipulate using this monitor. Let's see. Can we do this? Yes. Okay. So this is the gamut of sRGB. We've got the A and B axes there, and then we've got the white point here. There we go. Good. Next slide, come on. Okay, this one is a much smaller gamut. You can see it's smaller. This one is a little MacBook Air, and it has less of a gamut than sRGB. This one is a high-end one. As you can see, it's got a much larger space. This is a broadcast space, actually. If you go to a high-end cinema now, and it's got digital projection, it will use this gamut. It's a thing called DCI-P3. And I mentioned that because when we get onto CSS Color again, which we'll do eventually, I promise, you'll see that DCI-P3 is one of the models you can use. Okay, so now we need to distinguish between device-dependent colors and device-independent. So device-dependent is kind of what we use. We have this RGB value, and it looks different on my screen, and it looks different on your screen, it looks different on the projector. Have you ever seen people say, oh, I'm sorry, I don't know, these colors look great on my monitor, but on the projector they seem to be all different? That's device-dependent. Device-independent is where you say, here's the measured value, this is the actual color I want to produce, and then some piece of software converts it to the RGB values that's needed for the device you're using. So instead of having the same numbers everywhere and different colors, you have the same color everywhere and different numbers, which it calculates for you. How are we doing for time? We're okay. So I'm also going to talk about print a little bit because it's the same procedure. Does anyone know what this is? This background diagram, by the way, do you know what that is? Any suggestions? Is anyone awake? It's just that you don't know. Okay, that's fine, that's fine. This is a dot pattern. The thing is that the inks are opaque, they're not transparent. So if you put, say, cyan ink on top of magenta ink, what you see is cyan, right? You just covered one up with another. You don't get a mixture. They don't add together. Because this is relying on light bouncing off the paper, coming into your eye, and you can't cover them up. So you have this dot pattern, and you put them all at different angles so that hopefully they don't cover each other up too much. And you make a color by changing the size of the individual dots. That's the way it is. So how do you do this? Well, first of all, so remember when we're characterizing a screen, you measured red, and once you're done measuring red, you measure green, and then you measure blue. You don't have to measure the combinations, just the individual ones, because it's additive. If we know what red is and what green is, we can make any of the colors of mixtures because it's an additive color space. In print, it's not additive, so we have to do all the different combinations. Lots and lots of them, like that. We make all these patches, and we measure every single one. And once you've done that once, you buy a much more expensive instrument that has a robotic arm that measures them all like this, because it's really tedious otherwise. So you measure those, and then what that tells you is, for any given combination of cyan, magenta, yellow, and black, what actual color will I get? And you've got the measurement. And the problem you want to solve is the opposite. Given a particular color, how much of these inks do I need? Which is a 4D reverse interpolation. But the result is the same as on screens. You've got neutral grays, you've got accurate colors, you know how to mix up any particular color as long as the device can produce it, then you know what color to... If it can't produce it, you're stuck. I mean, you just can't produce more than it can do. And you can save all that data. Having gone through all that trouble, you want to save it somewhere. And you put this thing in an ICC profile. ICC is the International Color Consortium, and they're the ones that made print actually be reasonable so that you could go to different print shops and get the same result. And that data is stored in either XYZ or Lab as appropriate. Good. Now, finally, we get onto CSS4 Color. And now you'll understand, when I show you a piece of syntax, you'll actually know what it's for. So first of all, CSS3 Color. Here we go. We've got RGB, blah, blah, blah. And on a wide gamut screen, it looks correct, because that's what you mixed it up on. And then you look on an SRB screen, and it's too pale, because this is device-dependent color. Now, we can hack. We can use media queries for, and we can say, do you support DCI-P3? And if you do, woohoo, use this. That's really horrible. You wouldn't ever want to do this. Just hack in different values so that they look the same. No, instead, what you do is you use LCH, which I already showed you. The first number in LCH is the lightness, the second one is the chroma, and the third one is the hue, the angle, 0 to 360. And then the browser calculates. So on 4 different screens, you will see the same color. 5 different screens, you'll see the same color. There we are, that's the syntax. So we've got LCH, just like that. That's the simplest way. These are all numbers from 0 to 100, apart from the hue angle, which is 0 to 360. You can have decimals as well. You can have as precise as you want. This slash introduces the alpha. And if you have a comma, you can have a whole new color. In fact, you can have several, but this is a fallback. So if you don't understand this syntax, here's the sRGB value. So that's LCH, which is the easiest one to understand. We've also got LAB, which is much the same, functional notation. So ICC colors. By default, it's in sRGB for web compatibility. That's what we've been using so far. But we've got predefined display P3, which is a sort of a reasonably wide gamut. If you have a Pro monitor, it'll be wide gamut like that. It'll be display P3. Apple recently introduced some phones which are also P3. They've got some laptops which are P3 and iMacs and this sort of thing. It was actually Apple that pushed us to have this in the spec. So there we are. That's how you do it. You say what space you're using, and then you give the values. There's no commas between them because the CSS working group has a war on commas at the moment. We want to eliminate them except where they're used to have lists of alternatives. So get used to that because it's going to be a challenge as the browsers catch up. Rec 2020, by the way, is a huge ultra-wide gamut thing that was designed for 4K and 8K television. It displays almost all the visual colors. You're not going to see one of those displays for a long time, but you can actually use it. You can specify colors in it in CSS4 Color as well. And Media Queries 4, as I mentioned, can check for support. So you can basically say, do I have a wide gamut monitor? Because otherwise I won't bother, I'll just give you sRGB. But if you have got it, great, I'll send you the other stuff instead. And lastly, CMYK. If you're doing a style sheet for print, this is how you will do it. You have an at rule, same sort of thing as at font face. But in this case, it points to a color profile, an ICC profile, and then you can just use it. So I give it a name, foo, and then I say foo, and here's the values. And there's 4 of them, CMYK. That's it. And that's device-independent CMYK, actually. So again, you can send that to different printers, and it will understand it. Great. So this is all interesting. Can you use it? No. No, you cannot. I'm telling you about something because it's going to be important in the future, and because I've been trying for years to actually get it into the browsers. It's not in the browsers yet. Well, okay, I lied. It's in Safari Nightly now. Some of it. It's starting to get there. Google are also interested in some of it. It is shipping. It's been weird because for like the last 10 years, all of the major desktop operating systems have shipped with color management enabled as part of the OS. And I was like, great, can we get it in the browser now? A bit too soon, not yet. It's kind of specialized. Nobody really wants it. But now with these wide gamut screens, people do want it. But then before that happened, mobile happened. And so suddenly everyone had a little device this big. And did it have color management on it? No, it didn't. But now it does. Now it does. The newest version of iOS does, in fact, have color management. And the new versions of Android, which they haven't shipped yet, but they tell me they're going to, will also have color management. So we're back in the situation that the OS supports it. It's just a case of having syntax in CSS to let us use this feature. The first working draft of this was only in July, so it's fairly early days. All of the specs, by the way, from CSS Working Group are now on GitHub. So you can look at the spec, you can see the latest edits. As soon as an editor checks in an edit, you can look at it. You can look at issues. You can add your comments on them. You can file a new issue if there's something in the spec that you don't understand. File an issue, say, why is it like this? Why isn't it like that? People will talk to you. It's much more open now. It's a very good way to help specification development. And that's basically it. These slides are online on my GitHub. The spec itself, as I mentioned, is also on GitHub. And I also wrote some code in JavaScript that does some of the color conversion, so you can see how that works. That's it. I'm done. Hopefully that was useful.